أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. In the lecture series of Material Studio and within the course of hydrogen storage, we are at the lecture number 3. And in today's lecture, we will discuss about the thermodynamic and dynamic stability of a material, particularly in the context of density function theory simulation for hydrogen storage in perovskite type hydride materials. So before we go into definition, it is very important to understand why stability is so important in our research. Basically, in hydrogen storage study, we are not only interested in how much hydrogen a material can store, but also whether that material can actually exist under real conditions. A material may show excellent storage capacity in simulation, but if it is unstable, it will decompose or distort and cannot be used in practical applications. So, therefore, evaluating stability is a fundamental step in DFT studies, and without it, our results are incomplete and cannot be considered reliable or publishable. So the focus of this lecture is to clearly understand two key concepts. The first one is thermodynamic stability, and the second one is dynamic stability, and how we evaluate them in practical DFT calculation. So these concepts are essential because in any research study, especially for hydrogen storage, it is not enough to show that a material can store hydrogen. We must also prove that the material is stable and can realistically exist. So, for example, if we found some novel perovskite material with a hydrogen capacity uh, like 5%, 6%, or 7, 8, or even 9, 10, but if they are not thermodynamically and dynamically stable, as I mentioned, the results are, your results are useless. You will not able to publish it. So, let us begin with the thermodynamic stability. Thermodynamic stability tells us whether a material is energetically favorable compared to its constituent element. In simple word, it answers the question: does this compound prefer to exist, or will it decompose into simpler substance? In DFT, this is evaluated using quantity. Using quantities such as total energy, formation energy, and hydrogen adsorption energy. Among these, formation energy is one of the most important indicator. As you can see in the screen, uh, I just write the general formula for hydrogen. I write for hydride perovskite, but mainly if your material is changed, you can modify this. Okay, but this is the most general form. And so, to access the thermodynamic stability of investigated hydride, so I use this formula as you can see on the screen. So in this equation, the EX2MH6 represent the total ground state energy of hydride, which I obtained from DFT calculation, and the term EX, this one, the term Ex and Em correspond to the energy of elemental species, while X and M in their most stable bulk phases. The term EH2 is the energy of hydride molecules, hydrogen molecule, which is typically calculated in isolated environment. Uh, we must isolate hydrogen. We must calculate this energy in isolated environment. This is very strict rule. So the coefficient in the equation come from the compound. We have two compound, two atoms of X, one atom of M, uh, and three hydrogen molecule, which together give six hydrogen atom. And the entries expression is divided by 9 because they are total of 9 atom. And as we know, the general formula for this is X2MH6. So in the unit cell we have 2X, 1M, and 6 hydrogen atoms. So it's equal to 9. As we want the formation energy on a per atom basis, so that's why we divide it on 9. Okay, and the interpretation of this result is very important. If the formation energy is negative, it's mean the compound is thermodynamically stable and can form spontaneously from its constituent element. And on the other hand, if the formation energy is positive, the compound is unstable and tend to decompose. Therefore, a negative formation energy confirms that the hydride is energetically favorable, which is a key requirement for hydrogen storage material. And now, as I mentioned in the start, that we must provide both stability, thermodynamic and dynamic. So this is all about thermodynamic stability. So it's a very strict rule that the resultant energy should be negative. Uh, Now let's move towards the dynamic stability. While thermodynamic stability tells us whether the material is energetically favorable, and dynamic stability tells us whether the structure can remain stable uh, when atom vibrate. I mean, when atoms start vibration, so whether this structure, as you can see on the screen, can remain stable when atom vibrate or not. It is important to understand that atoms in a solid are never completely at rest. They are always vibrating due to thermal energy. So therefore, even if a material has low energy, it may still be unstable if its structure cannot why it is these vibration. So dynamic stability is evaluated in DFT using the Phonon dispersion calculation. In this method, we analyze the vibrational mood of crystal. So, and the key condition is that all the phonon frequency, as you see on the screen, must be real and positive with no imaginary frequency. If any imaginary frequency appear, it indicates that the structure is unstable and will undergo distortion or collapse. In simple terms, imaginary modes show that the structure is setting in an unstable point and will move to a different configuration. So, as you see in the screen, I calculated Phonon dispersion with the aim of to check the dynamic stability, whether the structure is dynamically stable or not. So I found there is no imaginary frequency. Imaginary frequency mean there will be no line appear below the zero. So no negative frequency, no imaginary frequency. It's mean that the structure under consideration BE2 BH6 is dynamically stable. So and also there is one other rule. So we have a formula, well-known formula, which is 3n, and these lines should be follow 3n formula. For example, if I explain the particular formula, like we have total 9 atom in a unit cell. So if we put 9 in these 3n, so we got 27. So it's mean these lines should be 27, not more than or less than 27. Okay, yeah. And at this point, it is important to understand the difference between thermodynamic and dynamic stability. Uh, Thermodynamic stability is based on energy and determined, as I already defined and explained in very clear way. But thermodynamic stability is based on energy and determine whether the material is favorable to form, while dynamic stability is based on atomic vibration and determine whether the structure can remain and take over time. Both are equally important, and a material may be thermodynamically stable but dynamically unstable, which means it cannot exist in reality. Similarly, a dynamically stable structure with high energy is also not favorable. Therefore, in a complete DFT study, both conditions must be satisfied. It's a very strict rule. So, and let us relate this to a perovskite type hydride. So, like for example, I will take X2MH6 or AbO3 derived structure. So we must carefully evaluate both stability criteria. First, we calculate the formation energy to confirm thermodynamic stability. Then we perform Phonon calculation to ensure that there are no imaginary frequency confirming dynamic stability. Only after satisfying both conditions, can we confidently claim that the material is stable and suitable for hydrogen storage application. I would like to mention that as the course is about hydrogen storage, so I'm relating the thermodynamic and dynamic stability with hydrogen storage application. So if you are studying up to electronic photocatalysis, catalysis, you should do thermodynamic and dynamic stability. And to make this concept even clearer, consider a simple example. So let's say, for example, we have a ball placed at the bottom of valley. This represents a low energy state which correspond to thermodynamic stability. Now, if we slightly disturb the ball and it still run to its original position, so it's mean the system is dynamically stable. However, if the ball rolls away after a small disturbance, it indicates dynamic instability. In the same case, in the same way, a material must not only have low energy, but must also resist structural changes under small perturbations. So, with this, thank you very much. And if anyone have any question, please feel free to ask. I would be more than happy to answer any question. Thank you. Take care.